Okay. So I wanted to welcome everybody, our guests both online and here in the room that aren't members. I did want to ask anybody that's a guest, if you just please raise your hand and maybe state your name. I'll start with you over here. Michael, welcome. Aaron, glad to have you. Let's see, I have a guest back here. Bruce? Jacqueline, glad to have you here. Thanks for coming. And gentleman here. Mike, thanks for coming. Okay, and then anybody online you'd like to introduce yourselves, come off of mute and say hello.
Tim, this is Fred Lusk with Central Valley Astronomers. How you doing?
Hello, Fred. Thanks for joining us.
Yeah, glad to be here.
And it looks like everybody else there are members, right? So great to see you all. Okay. The sheet for refreshments, get some housekeeping things out of the way. I'm going to pass this around. Members only are taking signups. Now that we're meeting back in person again, we can have refreshments. Mike and Doug hosted the refreshments tonight, but traditionally we've taken turns and rotated so that once a month our meetings, cookies or muffins or anything complicated, but it's appreciated, and we all kind of share that from month to month. So sign up on the sheet as it goes around, and you folks online will eventually get you to show up in person and get you to sign up as well. So, okay, so basically the meeting agenda tonight is fairly straightforward. We're going to jump right into the presentation here in just a few moments. And we've got a great speaker for you tonight. We'll be introduced in just a moment. After the speaker, we've got a short time for Q&A. Please interact and ask Dr. McKay anything that is relevant. And then we'll have a club part of the meeting where we do some announcements and some recognitions. And then basically at that point we adjourn. So that's the agenda for tonight. So I'm going to now ask Jerry to do our speaker presentation, because I think we're to that point.
Thank you, Tim. First off, Jeff Baldwin really wanted to do this introduction. He's had occasion to meet our guest speaker tonight. So yeah, he is sorry that he has to miss the meeting, and he has such a lousy internet connection that he won't be able to be here. So in Jeff's absence, it is my pleasure to introduce our speaker tonight. Dr. Chris McKay earned his PhD in I gotta get this all right, astrogeophysics from the University of Colorado in Boulder. He is at the NASA Ames Research Center now as a planetary scientist. His primary research interests are the evolution of the solar system and the origin of life. He's been involved in planning future Mars missions, which means on Earth he has to go to some pretty lovely places to try to simulate Mars, places like the dry valleys of Antarctica, the Arctic, the Namib Desert, the Atacama Desert. So he's been to all these because they have similar characteristics in some respects to Mars environments. So he's dedicated to his work in order to make all these trips. Excuse me? Question? He is a sought-after speaker, both professionally and in the public realm. I heard him myself on Science Friday on National Public Radio not too long ago, where he and another scientist discussed the possibility of life on Earth actually beginning on Mars, which is really cool. Cool idea. Tonight, Dr. McKay will be discussing two objects that have wandered through our solar system from elsewhere and talk about what that means for life, both here and possibly other places. So, ladies and gentlemen, please welcome Dr. Chris McKay.
Great. Hello, everybody, and it's good to talk to you, even if only virtually. When Jeff emailed me and asked me if I could talk, I was pleased to agree. I've talked to Stockton Astronomical Society many times before. In fact, I think starting in the 80s, late 80s maybe. So it's been a number of years. I think on a cycle of about 5 years or so, I used to at least drive out there and talk to you about what we're doing. And I always like to hear about your projects and your amateur ATM work in particular. Since I started my career as a making a mirror for a little 6-inch, and that got me into astronomy, and ended up doing what I'm doing now. So carry on the great work, and I'll probably be back in another 5 years. Okay, so let me see if I can share the screen, and let's see, share. Okay, you see this presentation called Interstellar Objects Passing Through the Solar System and Astrobiology.
Yes, we do.
Great. Okay.
Yes, sir.
Thank you. And I'm still not used to talking on Zoom, and so if occasionally somebody would just nod or say uh-huh, so I know that I'm not talking into the vacuum of space. When you give a talk in person, you can make eye contact with people, and it keeps me awake at least. I'm going to try going into, well, I think I won't try. I was going to go into slideshow mode, but that might be risking more than I want to risk. So I think I've got it so you can see the screen and read the words. And we'll just go ahead. Interstellar objects passing through the solar system and astrobiology. I start by the famous question, where are they? People had been looking for interstellar objects for a long time, and they had been conspicuous by their absence, really. They had the first discovery that I know of. Maybe the reason I know of it is because one of the co-authors was a fellow graduate student many years ago with me, Duncan Steele, was dust, small, tiny particles moving at interstellar velocities entering the Earth's atmosphere, 96. So people had been aware of the fact that interstellar objects would have extremely high velocities, and they would show up if we were tracking objects in our solar system or entering the Earth's atmosphere, but nothing. There was also some isotopic evidence for interstellar grains, particularly interesting interstellar diamonds, but nothing really to get excited about until 2017, when, as I'm sure you all remember, Oumuamua came through to much excitement and acclaim. There was really two very interesting things about it. One is it was a very unusual object, and the second interesting thing was that the next interstellar object, large object, came in just 2 years later. After waiting for years and years, they come bang, bang. It's like the bus bunching problem. I'm sure you've all familiar with it. You wait at a bus stop, seems like you wait forever, and then a bus comes and the same bus right behind it, and then another one. It's like all the buses come at once. What's with that? And it seems like interstellar objects are the same. But it's even stranger than that, because imagine you're at a bus stop and you're waiting for the first bus, and the first bus that comes looks like it's a flying saucer, right? That's the situation we're in. Oumuamua was so strange, and I'll come to that. And then the next object, Borisov, was just what you'd expect, a regular bus with blue trim and 6 tires. It looked just like you'd expect. The first one was so strange. The second one was exactly what we would have expected an interstellar object, large interstellar object, to be. And then the fact that they came bang, bang right after each other, it was also strange. So, I thought this is very interesting. Here's the trajectories of these two objects. The red is in Oumuamua, and the white is Borisov, comet Borisov, discovered by a semi-amateur astronomer, comet hunter. Both of them, of course, as you certainly aware, you can easily identify an interstellar object because its velocity coming through the solar system is much higher than velocity of comets bound to the sun. They have the infinity of very large. I'll get to that. Well, I got involved in this directly when when Astrobiology, the journal Astrobiology, got a paper, an unsolicited paper sent in by a rather well-known astronomer at UCLA, Ben Zuckerman. And the title of the paper was "Oumuamua is not a probe sent to our solar system by an alien civilization." That was the title of the paper. And I knew exactly what, and he wanted to know, he was sending it to me as an associate editor, deputy editor, and I knew him, I knew Ben from working with him on book projects. He said, would astrobiology be interested in publishing this paper? And I thought, well, that would be interesting. And I knew that there had been a sort of a controversy about the nature of Oumuamua. And he was responding to that. And I said, well, I talked to the editor in charge and I said, this would be interesting to talk about the astrobiology implications of these objects. And this paper has to be a response to a paper that says it is a probe, right? Because this is arguing the negative. His argument, Ben's argument, is very simple. And it kind of makes sense. You think of JWST and you can see the nature of his argument. He says his argument was, unlike what we thought in the 50s, aliens, any intelligent civilization is not going to investigate the galaxy by sending probes. They're going to investigate the galaxy by building telescopes, bigger and bigger telescopes. And if you want to look on the other side of the galaxy, you just make a telescope that is huge, much cheaper than sending a probe. And then you scan the sky with these large telescopes. And you can see that we're going that way. Imagine extrapolating from small telescopes in space to Hubble to JWST, extrapolate another 500 years, we might have telescopes that span the solar system in effective aperture, right? And imagine what they could do in terms of probing distant stars in the galaxy. So why send probes when you can build telescopes? That's the essence of Ben's argument. So I thought that was a good argument. I thought, let's put the editor-in-chief, Sherry Cady, said, yeah, why don't you put a special issue together? So the first person I called was Avi Loeb, who was the person at Harvard who had been arguing for an artificial origin for Oumuamua. And I said, well, Avi, if we do a special issue, would you be willing to write a paper? Because we already have the counterpoint paper, and your two papers would be the core of this special issue. And he said, yes, I agree. And he said, I agree with the notion that things should be discussed. You don't want to suppress a hypothesis just because it's not conventional. And great. So his argument is that should we consider an artificial origin for Oumuamua is, first, it is like an object. We've never seen a natural object like this before. No explanation for Oumuamua is like any other object that we know of in our solar system or seen anywhere. People have tried, and basically for the reasons listed below. It had non-gravitational accelerations, which comets have, but they have it because they have jets and tails. It had no tail or no plasma tail, no dust tail. Its initial velocity was 0 with respect to the local standard of rest of the local stars, which is not impossible, but unusual. And the thin shape without any coma, without any dust tail, we've never have seen before. And there's no object in our solar system that had this very thin shape, pancake shape, and was obviously not icy. And alternate explanations, obviously Avi's explanation is this is a derelict solar sail probe. Now, most recently, he has posted a blog saying, or maybe it's a fragment of a Dyson sphere, a derelict Dyson sphere that's broken up. Either way, it's artificial. The non-artificial explanations for the shape and the lack of a plasma or dust tail are also very exotic. They involve pure nitrogen icebergs or pure hydrogen, solid hydrogen icebergs. And those may exist, but in a sense, they're not any less exotic and alien to our experience than solar probes, right? So that it's an important point that we have no precedent for the nature of Oumuamua. It doesn't prove that it's an artifact created by an alien civilization, but it proves that it is, to our experience and understanding, a unique object. And it was, to me, it was all the more, the unusual nature of Oumuamua was all the more put in contrast by the very unsurprising nature of the next interstellar object, comet Borisov, which was perfectly normal looking comet. The only thing unusual about it is it was moving at very, very high velocity. So we put a special issue together. It just came out a few months ago. These two papers are in it, Avi's paper and Ben Zuckerman's paper. A lot of other scientists got interested and put in papers. We even put in a paper ourselves, as I'll come to. So it's interesting. And what I want to do tonight is not debate the origin of these objects, or what it is this really a space probe, or why did they come together, but talk about, is this a paradigm shift? So let's review what we know about interstellar material. Here is these first two objects, Borisov and Oumuamua. We also have an asteroid that may be interstellar. An interstellar meteorite reported, still being worked out. And of course, the interstellar dust, well established and published many years ago in isotope work. But to my mind, this is like ants in the kitchen. If you see a few of them, you know there are millions, right? And this should be the same here. If we see interstellar objects in our solar system and we've caught the glimpse of two of them, then we should expect them to be millions of them coming through, literally millions of them coming through. And we should be able to soon see them. The Vera Rubin Observatory Telescope, previously known as the Large Synoptic Survey Telescope, is a telescope which will be capable of detecting. It's been predicted that it should find, on the average, one interstellar object, large interstellar object, every month. And it does it by having a humongous field of view camera. Here's the public relations person of the telescope holding a diagram, and there's the full moon. You can see how big it is in terms of its footprint on the sky. The full moon looks like a small fraction of what this camera is looking at. So this is able to survey the entire sky that's visible at this site every 3 nights. And about half of the entire sky, 302 pi steradians, is visible at this site. This site is at 30 degrees south. So we're going to have a pretty careful survey of objects like this, and interstellar comets should pop out very easily from the data because they will be moving so fast, their velocity. And if you're monitoring them every 3 nights, that's going to be pretty easy to see. So there's predictions, and this telescope will come online in the next few years. And it's predicted it will find as many as one interstellar object every month. That will be incredible. And it maybe will solve the bus bunching problem. No one will care anymore. If we're seeing one a month, and the fact that we saw 2 of them in 2 years, it doesn't become extraordinary anymore. So what I want to talk about tonight is the question, is this a paradigm shift for astrobiology? The discovery of large objects exchanging between star systems, may be a paradigm shift in astrobiology in terms of transporting life between stars. That's the question that I'm interested in. And as you heard it in my introduction, I'm interested in the origin of life. Is it that we need to consider as a possible explanation for the origin of life, it came from another star? Now, I want to do a little history here. In the 1980s, there was just such a paradigm shift in astrobiology in terms of transporting life between planets, not stars, but between planets. I want to remind you of that. For me, it was very important because I graduated my PhD in the early 80s. And I had gotten interested in astrobiology a few years before that when Viking landed on Mars. And so this first paradigm shift, in a sense, rocked my world, literally and figuratively. And the rocks literally are these rocks, both examples found in Antarctica, but found elsewhere too, meteorites from Mars, right? You all may remember the big hoo-ha with Bill Clinton and all that for Alan Hill's 84001 and the possibility of evidence of life on Mars in that meteorite. But the real one that started this was not the one found at Allen Hills, but the one found at Elephant Moraine, EETA 79001. It was found 5 years earlier, in 1979. That one was really a paradigm shift in astrobiology, and I'll tell you why. Because that's the one that established that this whole class of meteorites that had been recognized as a class, it was studies of EETA 79001 that established that it was from Mars. And why do we find meteorites in Antarctica? Just to remind you, meteorites fall all over the place, but in Antarctica, they get concentrated at places where the ice is abutting an obstacle like a mountain, and ablation is removing the ice and leaving behind the solid material. It's a giant conveyor belt that carries meteorites from a large area and concentrates them in these blue ice fields in front of barriers like Elephant Moraine or Allen Hills. And you can go there and they just pick them up. And the fact that they're sitting on ice makes it easier to recognize. All the black stuff there is meteorites. So for that reason, we have now found more meteorites in Antarctica than the rest of the world put together. It's not that Antarctica attracts meteorites the way, say, trailer homes attract tornadoes. It's just that there's a concentration mechanism that makes them easy to find there. Okay, so why do we know that these rocks came from Mars? Well, there was a paper published in 1983 by Don Bogart and colleagues showing that the bubbles of gas in this meteorite, the little tiny bubbles of gas in this volcanic rock, the meteorite from Mars, or the EETA 79001 was a volcanic rock, and it had inclusions in it, and those inclusions contained gas, and the gas in those inclusions was identical to the gas in the Mars atmosphere as measured by Viking. So there were little balls of Mars, little bubbles of Mars air, and that's not Earth air, and it's not Venus air, and it's not Jupiter air. It was Mars air. The ratio of carbon dioxide, nitrogen, argon was distinctive to Mars. The only way to explain that is these meteorites came from Mars. And that was a shock. No one would have predicted that meteorites from Mars could be launched off that planet and come to Earth. Given this data, theorists quickly came up with an explanation for how it happened, but it was what you could call a black swan event. No one anticipated this result. It was a shock. And for astrobiology, it had a lot of implications. And here I want to discuss them. So meteorite ejection from Earth to Mars. The first analysis that showed the implications for astrobiology was some work done by Ben Weiss when he was a grad student at Caltech. Showed basically that microorganisms, if there were microorganisms inside the rock, they could survive the trip. The impact on Mars, the journey through space, and the entry on Earth, they would survive the trip. The interior, he showed by studying magnetic domains within the rock, that the interior temperature of this rock never exceeded temperatures above 50 or 60 degrees centigrade. The inside of the rock doesn't cook. And you know this, if you're a meteorite hunter, you know this. There's an ablation crust on the outside of a meteorite, but the inside is still cold from still at the temperature of space, if you get to it quickly, that is. Right? So what this meant was that Earth is not biologically isolated from the other planets necessarily. Panspermia becomes credible. And hence, if we find life on Mars, it could share a common genesis with life on Earth. The planets are exchanging life. Life could have started on Mars. Several people then quickly jumped to the conclusion that life could have started on Mars and been carried to Earth, and that for a lot of reasons, which I'm not going to go into, Mars might have been a better place for life to start than Earth. And this was a paradigm shift. I remember when Viking launched in 1976, the assumption was if we found life on Mars, it was a second genesis. It was alien life. It was on another planet. Of course, it's going to be alien. And of course, it represented a different type of life. The assumption was that life was a planetary phenomenon. And if a planet had life, it must have originated on that planet. And if there's life on Earth, it must have originated on Earth. Life started here on Earth. This discovery of this meteorite threw all that into question. And for me, I was interested in the search for life on Mars. It forced me to refine the logic of what I was looking for. I wasn't just looking for life. I was searching for and hoping to find a second genesis of life. So it was no longer enough to find life on Mars. We had to find life on Mars and prove that it wasn't related to life on Earth. And I think in one of my previous talks to you guys, I probably talked about this, the search for a second genesis. So in the 80s, the discovery of exchange of material between planets caused a paradigm shift in how we search for life and our understanding of the origin of life on Earth, and just the whole questions of life between planets. And it also said that panspermia is something we have to take into account. But it's often just thrown away. There's a couple of quotes from people who just say panspermia is garbage for no reason. I particularly like the last one. The last one is from a paper in theoretical biology that says, if the creation hypothesis, panspermia, and spontaneous generation are all set aside, so panspermia is being lumped in with creationism and spontaneous generation. Well, they may not like it, but it may have happened. The theorists of origin of life theorists, they want life to have started on Earth, but if it came here on a rock from Mars, that may be a historical fact we have to deal with. Right? So I'll come back at the end to how do we test what actually happened. Okay, so now the story's getting even more interesting. So Martian meteorites indicating interplanetary exchange. Timescales are short. Microbial survival is easily possible. Now we have interstellar objects suggesting exchange of material between stars. So in the 80s, we were coming to grips with the idea that material was exchanging between planets. Now we're forced to consider the possibility, well, the obvious possibility, that material is being exchanged between star systems. Right? Borisov is really the example. It, being a comet, here's a picture of it, it moves through our solar system and it left behind 10 to the 7 grams of dust in our solar system. So it came in at an incredible speed, 38 kilometers per second. That's its V infinity. As it comes in, it screams out, in and out, just passing through. That's what it says, just passing through. But it leaves behind tiny grains of dust in the tail. And these grains of dust are stopped by solar radiation, and they're still in our solar system. They're floating, just like we go through the tail of comets and you see fabulous meteorite showers. The dust of Borisov is bound in our solar system, and Earth will encounter that dust, maybe small amounts of it, as we continue in our orbit around the sun. Borisov came not within 1 AU, but the dust will slowly migrate in under radiation dampening of its velocity. So someday, grams of dust from Comet Borisov will land on Earth. So there is exchange of material from that interstellar object. Now, 10 to the 7 grams of dust is a lot of dust. It may not be very important in the scheme of the mass of the Earth or the Moon, but it opens up the possibility of what if that dust does contain organisms, right? So the idea that life may transfer between star systems has to be considered now, not so much because of Oumuamua, because there is no Oumuamua left nothing behind, as far as we know, but Borisov did. It left a lot of dust behind in our solar system. So what's the basic scenario? The basic scenario has been around for a long time, which is that an impact on a habitable world like Earth kicks stuff into space. It gets incorporated into long period comets. They get it as the comets move around the Earth, move around the solar system, and they get ejected by passing stars, become interstellar comets, and they go to another solar system. So it's a natural process for exchanging material between stars. The limiting factor is probably the ejection off the habitable planet. But there's no reason this shouldn't be occurring. Just like we know that rocks are coming from Mars all the time now. It's a natural process that's been going on over the age of the solar system. There should be interstellar comets exchanging material between stars over the age of the galaxy. Okay, very interesting. So we have to consider, if we're going to be intellectually complete, the notion that life may have come to our solar system from another solar system, carried on these interstellar transport systems, interstellar comets. So here's the outline of how this natural interstellar material exchange works. Impacts launch material from an inhabited world. That material is incorporated into comets. Gravitational forces, I misspelled that, sorry, and stellar encounters eject comets into interstellar trajectories. Comets enter a planetary system, and as they approach the star, they lose gas and dust, or they smash into a planet directly. And that's how you get interplanetary exchange. Now, as you probably know, there's been discussion, and I've been active in this, suggesting that we ought to send life to other planets. Not natural exchange via meteorites, but purposefully send life to other planets. And so our contribution to this astrobiology issue was a discussion of directed panspermia using interstellar comets. Okay, and my co-authors are Paul Davies and Pete Worden. So 3 scientists are happy to be on the lunatic fringe. So here we are on the lunatic fringe, considering why here is this natural interstellar transport system. Would you ever want to use it, and why? Let me talk about why. Right now, we are at the edge of just amazing discoveries about exoplanets outside the solar system. Kepler really broke open the field, and JWST and a host of telescopes, we're going to learn an awful lot. And it may be that we find a lot of habitable planets and no evidence that they're inhabited. We see a lot of planets that look like they have conditions for life, but no evidence of biomarkers, no evidence that life is there. And this could be the case if the natural origin of life is extremely difficult. Right? So the universe has a lot of empty houses. That's a possibility. I'm not saying we know that, but I'm saying that that is a possibility, that there are a lot of empty houses in the universe because houses, habitable worlds, are maybe easier to make than life. And to have a house, to have a habited world, you need two ingredients. You need a world that's got the stuff needed for habitability, and you need life to be there. And it may be that the pessimists are right, that n equals 1, and that we're it, and that Earth is not unique in the sense of a planet, but it's unique in the sense of a planet with life. And that Fermi's question, where are they, is answered simply by they're not there. There's lots of habitable worlds, but there aren't very many, if any, other inhabited worlds. I'd be very disappointed with that result, but we will have an answer to that question in a few more generations of space telescopes as we probe more and more carefully into the world's exoplanets around us. Life cannot hide. Life cannot hide. It leaves marks. And eventually we will see them if they're there to be seen. And if we don't see them, and we find many habitable worlds, Earth-like worlds, in the habitable zone of their stars, and we don't see any evidence of life, that may lead us to conclude that the natural origin of life is very difficult, and that we need to do something about it. And we may also conclude that spreading life is value, populating those empty houses. So we may decide to send life to other Earth-like worlds that are not habited. So what would we do? We could, but people have suggested before, there's a famous paper by Leslie Orgel and James Crick and Orgel, Crick of Watson and Crick in Discovery of DNA, suggesting that we build spaceships and send them out to spread life to other planets around other stars. And that's a common theme in science fiction, of course. But building spaceships is expensive. And you have to operate them, and it's hard to imagine that working. But here we have comets that are going naturally from star to star. Borisov left the Earth and is moving on to other solar systems. We don't have to launch anything to keep it doing what it's doing. But we could, say, hitch a ride on these natural interplanetary passenger or transport systems. So what would we do? We would launch material. So we see an interstellar comet coming towards us. We would launch a cloud of material in its path. It would fly through that material, and that material would get incorporated into the comet so that the next solar system it went, it could deliver that material, right? So panspermia directed panspermia would work to make the first two steps orders of magnitude more efficient, right? And how would we do that? Well, we would do it by putting together a biological payload. I call it an inoculum. That could be the seed. So we basically put seeds into these passing comets. We load them up with seeds, and off they go. We'd load them up with a diversity of seeds that would do well on Earth, do well on Enceladus, do well on Titan. They wouldn't necessarily have to be just bacteria. Think of tardigrades could be in the seeds. What else? Once we understand the list of environments on exoplanets, we could tailor organisms to fit into it, right? So, and these organisms could be inside the comet where they'd be protected for radiation. And in principle, they could survive. These seeds could be viable for millions of years, which is about the time it takes for Borisov to reach the next star, right? So, okay, this is all fun, but what would be the predictions? How would we see evidence that this is happening? that either natural or directed interstellar panspermia is happening. Well, first prediction would be we would see evidence for life on Mars that's related to life on Earth. Not because life came from Mars, but because both Earth and Mars were seeded by an interstellar comet. We would also see life in Enceladus related to life on Earth. We would see life in Titan, not directly related to life on Earth, but with a similar design similarity, because it would be part of this inoculum. And if we were to sample an interstellar comet, we might find in it these seeds, this inoculum, which would be of considerable interest. And there are missions proposed to sample an interstellar comet, right? So it goes back to the question that I'm interested in the first place. Where did life on Earth come from? And I would say, given right now, we have 4 working hypotheses, and there are advocates for all of them. The most commonly advocated one is life on Earth started on Earth in a deep sea hydrothermal vent. I would say that's the front runner. It can't be proven yet, but it's the one that most people would vote for. Too bad science is not a democracy. The second candidate is life started in hydrothermal vents on land, in volcanic vents, on surface hot pools. Think of Mount Lassen, hot pools around Mount Lassen or Yellowstone. That on land, but again on Earth. But then there's some folks who have argued, as I showed you in that citation to Steve Benner, life started on Mars and was carried to Earth by meteorites. And now we have a compelling case to consider at least the possibility that life started in another solar system and was carried to our solar system by comets. Okay, well, what would this predict? What would these different models predict for the distribution of life in our solar system? Let's call life on Earth life 1. We only have one example of life. It's us. We're number 1, of course. So we're life 1. If there was Earth-Mars exchange, and that was all there was to the story, Mars would also have life 1. And then Enceladus would have a different life 2. Okay. If there was a comet source, interstellar source, then Earth, Mars, and Enceladus would all have the same type of life. It would have been seeded by an extraterrestrial inoculum, natural of life. So we'd all have the same, we'd be our cousins. On Mars, if we found life, they'd be our cousins, and so would they be on Enceladus, and we could map them onto our tree of life. If life started on land on Earth, then Earth and Mars would have different life, and Enceladus would have no life. There's no land on Enceladus, only ocean, right? If life started on a deep sea vent, then life 1 on Earth, life 2 on Mars, and life 3 on Enceladus. That would be pretty cool. 3 examples of life right here in our solar system. Go life. That's the scenario I'd like the most because it gives us the most examples of biology to study, right? There's also the possibility I put here, none of the above. We don't have a clue. I said here are our 4 working hypotheses. They're all wrong. And we find no life, we find life on Earth. Okay, that's done. We find nothing on Mars and nothing on Enceladus. Now, I don't know what we make of that. We basically back to the drawing board. Right? But now I want to add directed panspermia, where life on Earth came from an interstellar comet as a result of action by some life form to instill an inoculum in a passing interstellar comet. Then the predictions are life 1, life 1, life 1, and life on Titan, related not directly but indirectly to life 1.
Let's go.
Okay.
Drop it.
Last slide, I believe. So what would be the technical signature, the technosignature of directed panspermia? Basically, it would be inside comets, we would find this mix of organisms, which would be not consistent with any one habitable world, which would be consistent with a range of habitable worlds. Different types of seeds put in. And the efficiency of the scope and efficacy of interstellar transport would be orders of magnitude larger than expected when it's undirected. Okay, that's the end. This slide is left blank. Left blank is my clue to end and open up this discussion for questions. And to encourage you all to keep searching for interstellar comets, because when you, as you all know, and every amateur astronomer knows, when you discover a comet, it's named after you. It is the only astronomical nomenclature system which honors the discoverer. You know, if you think about craters on Mars or the moon, they're only named after dead people. The only way to get something named after you when you're still alive is to discover a comet. So please get out your telescopes, monitor your patch of the sky, and discover an interstellar comet. I would love to hear about that. And that, I think, part of the motivation. Well, you all know Messier and his list was all about searching for comets. Well, why would he search for comets? He wanted the comet Messier, right? So good. I like that. Search for comets. Okay, I'm going to stop sharing and start listening, hopefully for some questions.
Do we have questions?
Yeah, so I saw one. I briefly had to step away for a moment, so I wasn't quite sure if it was answered. But my question was, before EATA and ALH meteorite, what was the generally accepted scientific theory?
For those meteorites?
Right.
Well, before those, the generally accepted theory was that meteorites came from the moon or from asteroids. You know, if you think of most meteorite classes are linked to a particular asteroid. You know, I think of the meteorites at Tatwini in the desert that traces back to a particular eukaryote, a particular type, because we have pieces of we have spectrum of the asteroids, and we can look at the spectrum of these meteorites and we can see the match. So the so-called SNC meteorites were anomalous because they had not been tagged to a particular parent body, right? But the general theory was that the parent bodies were the moon or asteroids. The idea that Mars could be a parent body was not apparent. It was
Wow.
so that was a shock that Mars could be that was shock number one. Shock number two was that the impact ejection on Mars, the transit through space, and the landing on Earth would not be enough to sterilize the interior of that rock. That's piece number two, and then everything falls from that, right?
Thank you.
Yeah.
Okay, I've got a question. Is there any reason to think that any of the organisms that we think existed on Earth could last the 1,000,000 years or more it would take to be interstellar?
Yeah.
Coming
Yes.
from Mars. Okay, there is evidence.
Yeah. That's a very good question. That's a key question. That's one of the questions I
Tardigrades
didn't.
don't live that long.
Pardon?
The tardigrades, do have a
Yeah.
finite.
Right.
life.
But the answer to that question is yes, and the reason is we have found on Earth one of the projects I worked on, in fact, was going to Siberia. The Russians had found in ancient permafrost, 5 million years old, frozen microorganisms that were still alive, frozen for 5 million years. And so one of the projects I was involved in just at the end of the Cold War. In fact, on one of our field trips was when Gorbachev was abducted and the Soviet Union fell apart. the Soviet Union was opening up, and we had an opportunity to go with them to Siberia and drill in this old permafrost and make radiation measurements in the permafrost. What I did was made radiation measurements in the permafrost to show that these organisms would not have been cooked by radiation while they were frozen for 5 million years, deep down in the permafrost. And as an exchange, the same Russian scientists came with us to Antarctica, where we drilled into permafrost that is dated 25 million years in the dry valleys of Antarctica. And in both cases, we find organisms preserved and viable because they're frozen, deeply frozen and buried, so they're protected from cosmic rays. So yes, microorganisms, if frozen to low temperatures, can survive. We know it from direct measurement for tens of millions of years, and maybe much longer, and it's because they're frozen, inactive, just sitting there doing nothing, and there's not enough radiation to kill them. What kills them, if an organism is deep frozen, you can put a microorganism in liquid nitrogen and revive it. So in liquid nitrogen, so let me back up a bit. There's two things kill microorganisms. One is thermal decay. They're just random decay of molecules. KT is what a physicist would call it. E to the minus E or delta E over KT. Thermal vibrations and thermal energy. Second law of thermodynamics. Think of it that way. The second thing that kills microorganisms is radiation, cosmic rays, high-speed bullets. Not the second law, but high-speed bullets coming in and tearing up molecules. So if you want to live forever or be alive forever, you have to set your temperature to 0 so that the second law of thermodynamics doesn't kill you. And you have to have 0 exposure to cosmic rays or any radiation. And cosmic rays is the big source, but there's also natural radionucleotides, uranium and thorium in crustal rocks, and there's also radon gas everywhere. If you block all those out and get the radiation dose really low and temperature really low, then in principle, there's no limit to how long you can remain viable. It's conceptually the same as being at liquid nitrogen temperatures, in which all motion has ceased, and then being warmed up and being viable again. There's no need for continuity, like a human being has a need for continuity. Don't try this at home. But for microorganisms, they can do it. They don't need to have a metabolic continuity to stay alive. So I think the answer is yes, based on the data we have in our theory and not. And that's why I mentioned that they need to be inside the comet to get the benefits of radiation shielding. Because even beyond the Earth's, beyond our solar system, there's still cosmic rays in space. So they need to be very cold and interior to the comet, a couple meters below. So when you inject the inoculum, it has to be injected in a way such that it takes it inside the comet. So that's a very important point. We discussed this in more detail in our paper. We also discussed, by the way, which I didn't touch on here, the same issues that arise on Earth called planetary protection. As you probably know, when we explore Mars, we try to not contaminate it on purpose. Some people have argued once we decide there's no life there, we might contaminate it. We try not to contaminate it accidentally. We might contaminate it on purpose, but we're not there yet. And you have to take the same approach to interstellar panspermia. You wouldn't want to send life to a planet that already has it, right? And so how do you ensure that that doesn't happen? Especially if you're not there to trigger the release. And so we discussed that. It's a very hard question. First of all, how do you know there's no life there? As you're getting closer and closer, you've got to have some way of figuring it out. The answer we came up with, which is not entirely satisfactory, is that you trigger a delay in the revival of the inoculum. So the seeds don't sprout. They're programmed to sit for a while. And the assumption is if there's life on a planet, and seeds drop from space, they get eaten, right? Manna from heaven, let's eat it. It's lunch. It's one thing on Earth. You drop sugars or organic material down. If it doesn't defend itself, it gets eaten very quickly. So that was what we came up with, but we appreciated the difficulty and do not claim that our final answer was an ultimate one. But it's an important part of the thinking, and it is on Earth. There's a lot of parallels between our interaction with other planets and now with stars. That's the second paradigm shift. Astrobiology became interplanetary in a complex way in the 80s, and now it's becoming interstellar in a complex way because there's natural exchange, which opens up the idea of artificial exchange and opens up the idea of worrying. It also opens up the idea of protecting us from natural exchange. If we knew that there was a rock on the way to Earth from Mars that contained organisms, Martian organisms, that were hazardous to our environment, we would want to stop it. Right now, that's probably not a high probability, but it's part of the thinking here. This natural exchange may not be something we want to allow to continue. Just throwing that out there. We are already trying to stop impacts on Earth for other reasons, but we might be stopping impacts on Earth for the reasons of not having anything carried here that we don't want carried here of a biological nature. Okay, other questions? We may have a little more time.
Dr. McKay, I have one more question. You mentioned that if it's ever determined that life doesn't exist on Mars, the general consensus is that, we could purposely contaminate the planet's surface. So the question that just kind of popped in my head is, what would be the organisms that the general scientific community would want to send to Mars, be it tardigrades or other microorganisms?
Well, I wouldn't say that there's a general consensus. That might be overreach. I would say there hasn't been much thought about the question. I remember giving a talk a few years ago in Death Valley, because I was there for a field trip, to a public audience about life on Mars and the search for life on Mars. And a fifth grader asked me, well, what will you do if you find life on Mars and it is a second genesis? And I said, that's a very good question. And the answer right now is we don't know. We spend a lot of time thinking about how to search for life on Mars and virtually zero time thinking about what do we do if we find it. It's kind of like the dog chasing the car, right? What is the dog going to do if it catches the car, right? It doesn't have a clue. We're like the dog chasing the car. We're going to Mars to search for life on Mars, and there's been virtually no discussion of what do we do if we find it. And it is a second genesis, or it's not, or it's dangerous, or it's not dangerous, or we're dangerous to it. So I wouldn't say there's a consensus that we should, if we don't find life on Mars, or we convince ourselves there's no life there, that we should introduce life. But that would be my opinion. That's the one part of the equation that I see clearly. If we go to Mars and find compelling evidence that there is no life there and never was, then I would argue that we spread life from Earth on the basis that life is an intrinsically good thing. The intrinsic value approach to environmental ethics, intrinsic value of life. That's the only part of it I think that's clear in my mind. If we find life that is there, what do we do? That's a very hard question. And it's got to do with, is it a second genesis? Is it microbial? I've heard people say, well, if it's microbial, who cares? Put them in a jar, stick them in the lab, and let's get on with the colonization of the solar system. I don't know if that's a good answer, but I certainly would not subscribe to it. Nonetheless, I kill microorganisms by the thousands every day when I brush my teeth and take a shower, and I have no remorse for that. I'm going to do it again tonight. The evil doctor laughed his evil laugh as he planned killing thousands of microorganisms on his teeth. Right. So why should we care any more about microorganisms on Mars? Well, I submit that if they represent the only example of a second genesis of life, they deserve a lot more consideration than the microbes on our teeth causing plaque. Okay, but that's a kind of a digression. We could have a complete separate discussion of environmental ethics as applied to space exploration. That's an emerging field, by the way. The literature on it is no more than 20 years old, and it's going in some interesting directions. And I think the interstellar connection will be coming in. I would submit, in all due modesty, that our paper is the first to really come to grips in a serious way with the environmental ethics of interstellar transfer of life, both random and directed.
Okay, thank you for that excellent presentation. A couple of us were having a discussion the other evening about virology. Can you hear me okay?
Garbled.
It's on. Okay. A group of us were having a discussion the other evening about chirality and left and right-handed molecules. Is there any current research that indicates there's anything other than left-handed molecules that are supporting life? And if we did find a right-handed molecule that supports life, would that be indication of a second genesis?
Yeah, that's a good question. That's a really good question. There's two parts to the question. Could life, so let me give some background. In your body are proteins made up of amino acids, and all the amino acids in your proteins are left-handed. This is my left hand. They are not right-handed, mirror image, right? In contrast, the sugars in your body are right-handed, right? They're not left-handed. There are sugars that are left-handed. So biochemistry naturally prefers to select one type of chiral molecule. If it's working with chiral molecules, it works with only one-handedness. And the reason is it's easier to make chains if they have, if everything is handed. And you can see this yourself. If you want to shake hands with somebody, right hand to right hand works, or left hand to left hand works. But if you try right hand to left hand, it's hard to grasp the person's hand, right? If you want to make a chain, link right, right, left, left, right, right, left, left. So when life is making chains like proteins, which are chains of amino acids, it wants to use only the same handedness. There's no reason to think that life couldn't make proteins with right-handed instead of left-handed. Why life on Earth has L instead of D is a question of endless debate. I just was reviewing another paper about it a few weeks ago. We do not have a consensus explanation for why life uses L or D. The explanations range from set by supernovas and early bipolarized ultraviolet radiation, or random. You got to do one or the other. It's like driving on the side of the road. You know, why do we drive on the right-hand side of the road? It's random. Some random point in history, we all decided to drive on the right, and we're stuck with it now. Other places randomly selected the other side. And the logic is the same. If everybody drives on the same side of the road, it's much more efficient. Right? You can drive everybody on the left or everybody on the right, but you don't want to do what they do in Rome, where they drive on both right and left. Then it's just chaos, right? So then the question is the important part of the question was, if we find life on, say, Mars, and the amino acids there are, and the proteins are right-handed instead of left-handed, what does that mean? There was a time when I would have argued that that meant it was a separate origin of life, a second genesis. But I've since become convinced by biochemists that we're not so sure of that. We don't know if chirality preceded the origin of life. In other words, if chirality was a requirement that led to life, or if it was a result of life, biological evolution. You know, to use an example, you know, humans have two hands. But if we found organisms on another planet with 3 hands, we wouldn't argue that that represented a separate origin of life, because we know that 2 hands is just a particular biological invention somewhere along the evolutionary history, right? Or another example is the blood types, A, B, O, and so on. They were just biological inventions, not prerequisites to life itself. And some people have argued that chirality, that life may have started off mixed left and right, driving on both sides of the road, right, in the Italian style. And then through evolutionary processes, it optimized to one side of the road or the other. And so there would have been a phase when life was not chiral. And if life on Earth and Mars split early enough, we may still be related. They may be related to us back in the days when we were achiral. So it's the whole question of how do we prove that life we found on Mars really is a second genesis is very hard. And that's one reason why I'm a big fan of Titan and Dragonfly. I'm a COI on the Dragonfly mission going to Titan. And maybe if we're still around in 2034, after that mission has landed, I'll give you a talk on the results. One of the goals of that mission is to search for life that lives in liquid methane. Liquid methane, not water. Well, there's no way life on Earth is related to life that lives in liquid methane. That is such a profound difference that it is sure a second genesis. None of our ancestors ever lived in liquid methane. I can say that with certainty, all the way back to the first primordial cell, right? So that's why for me, the best possible outcome of exploring the solar system is finding life on Titan by the Dragonfly mission in the year 2034, yeah, when it lands, or is it 2037? I forget now. That lives in liquid methane and metabolizes hydrogen. Because not only would that tell us that we found a second genesis, and as 2, it would be a clear second genesis. And it would say not only is life widespread in the galaxy, but that it's widespread and it can be weird. Now, we don't know if they're weird or we're weird because we only have one of each. We don't know who's normal. When you only have 2 things as different as water and liquid methane, you don't know which one's normal and which one's weird. But we know that they can't both be the same. They're not the same. So anyway, yeah, it's a tough question. How do we, is chirality a sure sign of a second genesis? It's not so sure. Maybe we have time for 1 or 2 more questions. Or not, that's fine too.
Do we have any questions online?
Yeah,
I
have a
don't personally
question.
have.
I had a question
Okay.
about comets. Has there ever been evidence of comet dust making it to the surface of Earth?
Oh yeah, yes. There is a lot of evidence for dust in the solar system to come to Earth. In fact, it's a field of study because it's a very easy way to get material. You can even collect it yourself in a bucket and water. I remember somebody's reporting on catching the water from the rain gutter and then searching through it for interstellar particles. And I'm trying to remember exactly how they sorted out the interstellar particles from the crap that's just been blowing around. It's slipping my memory. But if you search on how to find interstellar particles in your rainwater, you'll find interplanetary dust particles in your rainwater. You can find them. I think one of them is searching for metallic particles. It's one way to find them. So yeah, and NASA had a program for many years of a high altitude airplane that would fly up in the stratosphere and collect the dust particles. Because then you know that way high up, it was the U-2 plane. It flew way high up collecting the interstellar dust. And some of that would come from comets. So a comet, when we pass through a comet swarm, a meteorite swarm, through a comet, a path of a previous comet trajectory, you see meteorite showers, and dust is associated with that too, and they would collect it. So indeed, and it decelerates very quickly, so it doesn't burn up in the atmosphere because the surface area is so high. It slows down very quickly and it doesn't heat up. Okay, how about one more question? Since I know we had at least two on the, or not, that's fine.
Anyone else? Oh, it looks like we're good. Dr. McKay, this was quite awesome. I could listen to another hour of this.
That's an interesting topic. Stay tuned. Watch for comets. Interstellar stuff is on its way, and we're getting to the technology where we're going to see them, hopefully, flying through one a month. That would be really cool. All right.
Quite awesome.
Yeah.
Thank you again.
Pleasure.
I'm sorry, but if someone's talking, we can't hear.
Okay. Laura, can you hear me now? Okay, my apologies. We're getting this whole Zoom and hybrid meeting in practice here, so we're working on it. Okay, I have a few announcements and a couple of things to do. So Eric, will you start the slideshow? And we'll use that. Okay, so okay. While we're waiting here in the room, does everybody have a raffle ticket or a prize ticket? So hang on to those. Jerry, thanks for doing a good job with that. Okay, Eric's sharing the PowerPoint with the Zoom and on the screen here. So let's give him a moment. Raise your hands if you've seen the comment. Raise your other hand. I had to see the comment. Yeah, I surrender. Yeah.
Good try.
Yeah. All varieties. Okay, so can you folks on Zoom see the PowerPoint, the slideshow now?
We did briefly, but it went away.
Okay, Eric's still working with it here, so we're gonna. It'd just be so much easier if y'all just showed up to the meeting. That's kind of really the bottom line here. So
We appreciate you no matter.
Oh, that's, thank you, Bill. Yes, we appreciate you joining in whatever manner. So. I mean, I can talk through it without the slides, but it'd be so much better with the slides up.
Oh, there it is.
You can see the slides now.
Oh, it went away, but we saw it.
How about now?
Perfect.
You can see it, Michael?
I can see it. Yeah.
Okay, good deal. So at the January meeting at the installation dinner, we always traditionally recognize all of our volunteers that have served the club and done public outreach for the past year. We unfortunately were under a real time crunch, and our apologies. So we're circling back here now in February, acknowledge those volunteers. So both online and in person, I'd like you to stand up if 2022 attended, participated in any of the public outreach star parties, the Oak Grove, the school star parties. Please stand up now. Or if you're online, raise your hand. Okay. Eric, I think you need to be standing. Oh, you're busy? Okay. Yeah. We want to recognize you all and thank you so much for everything that you've done. The public outreach events have been tremendous. It's evidence because we're getting asked to come back and do more and more of them. So thank you all for your contributions and everything you've done, and keep up the good work. So appreciate you and give you a round of applause. And I've got some choice. Let me just point out the ones that are really working here. Bill, you can see, is standing up, giving instruction at his telescope. So is Eric. Here, Eric's staring into the sky. I'm not sure what he's looking at, but you see, Mike had the presentation down really well. Seated, reclined position. So, yes. But yeah. What? Yeah. Yeah. Okay. And if you go to the next slide, then please. Eric. Everybody cross their fingers. I just have one other acknowledgement and appreciation that we again didn't get in January. There we go. So two of our members, Ed Reibel and Jeff Baldwin, have, amongst others, but I'm naming them here because they've done an extensive amount of work with San Joaquin County Office of Education and the Sky Mountain Astronomy Program, which I think many of you have heard about. But I just wanted to give a shout out here and recognition to Ed and to Jeff. Unfortunately, neither one of them are here or even online. But these two guys have done so much work. They've taken telescopes up there. They've written instructions and night sky. And that program is kind of in its infancy and getting started. But we really want to thank Jeff and Ed. The secret thing about it is that association and that relationship that they built made this room available to us. So really want to give Jeff and Ed a round of applause. And they'll have to watch the recording to get the true appreciation. So, okay, yeah. Eric, can we go to the next slide now? Just have a couple more announcements. We have a new social media chairperson. a kind of new position for the club, but Keys is now in charge of Facebook, Instagram, and all things social media. If you see something that has been posted, probably come from Jason, that you think the club should be posting or getting out there into the social media world, contact Jason and he'll take care of it. He looking forward to a lot of good things from Jason. And by the way, we need to also congratulate Jason. I don't think he's online, is he? Yeah. He and his wife Laura just had a new baby girl. So congratulations,
Aw.
Jason. Yeah. And also here's Jeff's name again. He has volunteered to be our Star Party coordinator for both Highway 4 and high altitude. So I wanted to recognize Jeff. Again, you should be seeing from Jeff our upcoming Star Parties. His goal is to promote them and get more participation in the Star Parties and get you all out there in the dark skies and doing some real earnest observing. So those are the two new positions we've got in the club. And then the next one, Eric. On kind of a sad note, this is a little bit belated news. I think many of you knew that Don Mockholtz had passed away in August. Don was you would call him a sincere friend of the club. He had presented to the club many times. He was local here in California, and I'm not sure if he ever visited in person or if he did. Okay. I got to know over the last few years, and I admired his observing habits and his discipline in hunting for comets. He was the discoverer of 12 comets. And as you heard Dr. McKay say earlier, the comet hunters are the ones that are really out there doing the science and gaining these stellar comets. And Don had 12 to his name. I think there's only a few other people in all of history that have more. I think there's somebody that has 15 or 16, but Don was right up there with them at 12. There's two here. I grabbed some snapshots of ones that he discovered in 1986 and 2004. So we wanted to remember Don and all his contributions to our club. And you can still listen to his podcasts and look him up on the internet. So Don's legacy will live on forever. So. I'm sorry, was there a comment? Okay. I think I just have one more slide that I'm going to share with Doug. If you want to come up here, Doug, I'll get started. On the left-hand side, the slide here are the upcoming SA meetings and Star Parties. You can all find these on the SAS website, on the calendar section of the website. Eric does a great job of keeping that up to date. The upcoming Highway 4 Star Parties and the high altitude party. And then we'll be back here again and on Zoom for the March 9th general meeting. Jeff's holding an ATM in March on the 11th. And then we've got March 18th. He's still deciding whether we're going to go to Highway 4 or high altitude. We'll see what the weather looks like on March 18th. So with that, that's the announcements for the meetings. And I'm going to turn this over to Doug now for the public outreach events.
Okay. All you people out there in Zoom land can see this also. This list here, public outreach events, is only the ones that are solidified. I've got 4 requests for school Star Parties also. Now, this can't be the Bill and Eric show on all of this. So if we're going to do these things, I have to get buy-in from everybody here, and you get people out there in Zoom land that have telescopes. We need you guys to either pipe up now and say, I can handle this one and this one? Or this evening, take a look at this slide here and download it or whatever, and pick 2, 3, 4 of them, you know, one every month at least, and which ones you can do. So I need volunteers. I need to know this stuff as soon as possible so that I can contact these people back and say, yes, we will be there. And I will also send out another email with the school start parties that are coming up with the dates on those. I should have done that today. I just got tied up at work. So once again, all you guys start, you know, which ones can you guys do? Because we cannot, like I said, Eric and Bill can't do all of these. Yeah. Somebody besides Bill and Eric, come on, guys. Which ones can you guys do? There's Bill and Eric, and there's Tim. Yeah, you know, huh? You're right, you know. Well, the ones on the same day, if you look, this is in the morning, and these are in the afternoon. Those are morning and afternoon. It still makes a long day. So, like I said, we're gonna need help.
Yeah, I may be able to add to that.
Yeah, the board got together and we saw all these dates coming up that we knew Doug was going to need help. And so we were trying to strategize, well, what can we do to encourage the members to come out and participate in these public outreach events? We thought, well, are there awards or recognition, or, you know, what's the carrot that we can hang out there? And we really came to one conclusion, and Bill's going to share that conclusion with you as to what the reason you should be coming out to these public outreach events is.
Yeah, I only hope that I can convince you here. There are a few people, and I know everybody that's been out here, and thank you very much for coming out to help. The Discovery Challenge Academy, Darlene and Frank over there are there with Eric and Doug and I, and that event alone are, I think it's 350 individuals looking through our scopes. Yeah, at one night we have 4 scopes, and it's very organized. But this particular event here, the 8-time thing, and what we discussed was the joy of outreach, and what do you get from going out there and showing your scope off to people. And some of the comments and reactions alone when somebody looks through the eyepiece and sees Jupiter or Saturn for the first time, where they're actually distinguishing the rings around Saturn and seeing colors. And how many different folks have looked through our scopes? Doug and Eric, you know, if I said 2,000, that is, you know, that's different people. We've had over 2,000 people looking through our scopes. So yeah, that would be in a year. So some of the things that stood out to me was there was one lady that actually started crying next to my scope after looking at Jupiter and seeing Jupiter for the first time. And another one, there was a small child after he looked at the moon through the eyepiece, and we asked him, what did you see? And he looked at me in the eye and he said, circles. He saw the crater and the moon itself. And so he saw circles, you know, and so I'm going to remember that for the rest of my life. And Eric, if you would go to the next slide. And this isn't the best picture in the world, but I've saved this picture. This gentleman right here, this is my scope. You see a young Eric over there. This is at Delta College. And that individual looked through the eyepiece and saw Saturn for the first time. And he didn't say anything. He just stood up and that big old smile on his face. And he still didn't say anything when I asked him a couple of questions about it. He walked over to his friends and just said, you know, you got to look through that. So I would go so far as to say, when we're out there in these outreaches, some of the best views I have ever had of the brighter objects, the planets and such, have come at the outreach. There was a time where you and we stuck the Barlow in right here in Stockton at one of the no, it wasn't at the college. It was at the Commons or something. O'Connor Woods. And that was one of the best views of Saturn that I ever had. And my question to you is, you know, especially with the weather that we've been having and such, and you're waiting around for a new moon. And okay, well, that got scrubbed because the weather sucked and you're not going to be able to go up. So we'll wait for next month. Next month doesn't happen. Outreach gives you an opportunity to go out there and get your eye into the eyepiece. You could go see stuff. If it's a question that you don't have a scope or something, maybe Tim can swing something and get you a scope, you know, from out of the closet that we have a bunch of scopes, and we could teach you to use it. And we'll put you right next to one of us or something. And so that's my plea to you. And that is why I do outreach. It extends my time, my eyepiece time, looking at the heavens. And we could help you out. If you feel uncomfortable, don't feel uncomfortable. We could help you out on it. That's all I got.
Jobs. So yeah, plenty of dates for y'all to get involved with public outreach. You know, one of the ideas that we had was many times the younger generation, they'll come up to our telescope and they'll pull out their phone, right? And they'll spend minutes trying to take a photograph through the eyepiece. You know, 9 times out of 10, it doesn't work. But the one time that it does work, they are just so thrilled with that. So one of the ideas we had was we're going to set up a scope out at Oak Grove, just looking at the moon, and set that scope up with one of those devices that holds the iPhone right in focus, so that maybe we just need a volunteer to man that scope to help the kids take pictures of the moon with their iPhones, because they'll go away with that photograph and they'll remember that for a long, long time. So, okay. I think that concludes just about everything that we have. We have till 8:30. We've got a curfew that we've got to be out of here, all tidied up. So we're right on time. We're 8:05. So we're going to adjourn here in just a moment. Everybody on Zoom, Fred Lusk. It's good to see you, Fred.
Good to be here. That was an interesting presentation.
Fred, I'm going to take the opportunity while I have you on the line here to tell us any news you can tell us about the Glacier Point Star Party plans for this year.
I still have not heard anything, and I'm not sure what's going on with that. Our Star Party coordinator is supposed to be checking into it. So at this point, I don't have anything. I think they're still working on Glacier Point Road.
Are they? Okay. I thought it would be done that way.
Well, it's a government project, so.
Yeah.
I do want to.
Keep us informed.
Yeah, I do want to. I'll publicly thank Jeff Baldwin for letting me know that Mars was doing a grazing occultation down in my neighborhood, and I helped him set up figure out place to observe. He ended up near the town of San Joaquin. I ended up in the mountains, and he and I both did videos of a grazing occultation. His was focused better than mine, but he had technical problems. But if you go onto YouTube and look for Mars Graze, Jeff's got a video up there, and I've got a time lapse that I put up there. So I took 22 minutes of video and shrunk it down to 1.25 minutes.
No, I didn't know you were there with him. I saw the video, and Laura, you were there as well, correct?
I was at a different location. I was actually up in the mountains.
Oh, I see.
Yeah.
Well, Fred, yeah, absolutely stand. But your club at Fresno as well, please.
Yeah. Yeah, I was actually the
Thank
only
you.
one from the club who went and saw that. So I pitched it, but wanted to come join me.
Okay, so for those of you in the room here, we've got a couple of prizes. So pull out your tickets, and the first prize, Jerry was going to tell us the winning numbers here. Okay. Get your own now.
Six, 3, 7. Oh, this is great.
Right. Dennis the clerk. Okay. Christy, are you into science fiction? Some. Okay, let me give you this book. This is an Arthur C. Clarke book called Return to Rama. And it's particularly related to tonight's presentation. That's right. That Rama that Arthur C. Clarke wrote about was an alien spacecraft from another solar system come to visit our solar system. Science fiction, right? But when Oumuamua was first discovered, it was actually named Rama after Arthur C. Clarke's science fiction story. So hope you enjoy the book. Good. And then Dennis, we've got this photograph of the Earthrise, the historic photograph taken by the Apollo 8 astronauts as they orbit the moon for the first time in 1968. With that, I just want to thank our guests for coming. Our speaker is now gone, but thank you for coming. And then everybody, I want to thank Eric Holland for the great work on the audio visual in the Zoom meeting tonight. And then if there's no other business of the club, I invite you all to enjoy some coffee and snacks, and I'll adjourn the meeting.
I have one comment, if you can still hear us.
We can. Go ahead, Laura.
About that book, The Return to Rama. It's pretty pornographic, honestly.
Uh-oh.
I
Christy, you
was,
got it.
it was co-authored by one of the other people from JPL, and it was very different from the first one. I mean, you're probably going to really enjoy it.
Now she's interested.
Yeah, no, we'll expect a full report, Christy.